In this video, we'll be talking about model evaluation for classification tasks and how the confusion matrix is used in this process. Recall that model evaluation is an important step that happens in between model training and production, and depending on the type of problem at hand, whether it's regression or classification, how you evaluate your model changes. We discussed in a previous video that in regression tasks, we use certain metrics, commonly the R-squared score and the root mean squared error, and in this video, we'll learn about the ones used in classification. These include accuracy, precision, recall, and the F1 score. But before we talk about any of these, we have to first understand an important concept in classification: the event class. The event class refers to the class that is of interest to us. In other words, it is the class we are trying to learn. Oftentimes, it is the minority class, and we specifically label it as the positive class, or more formally, the class where the label y is equal to 1. Examples of that can be seen in marketing, where the positive class is customers who churned. In fraud detection, the positive class is fraudulent transactions. And in medical diagnosis, the positive class is the diagnosis of a disease, and so on and so forth. And because we have control over the label y, we have to be very careful with how we choose them, and we'll see why shortly. Now, suppose we worked at a bank, and we're tasked with creating a machine learning model that helps the bank determine whether a new borrower will default on his loan or pay it back fully. We are given a sample of 16 borrowers, their annual income, the loan amount, and whether they defaulted on their debt or paid it back. The first step here is to label our target variable, and because the event we want the model to learn is default, we will map defaulted borrowers to class 1 and safe borrowers to class 0. Now, recall that to tell if our model is a good model, we need to evaluate it, and to do so, we'll have to split our data into a training set and a testing set. We'll train a simple logistic model using the training set, then get rid of this data and bring in the testing data we saved earlier. And because this is testing data, we do know the true class of these borrowers, whether it's positive, meaning they did default, or negative, meaning they paid back their loans. And because this is a classification task, the model will either predict them to be positive or negative. To find out how the model performed, let's feed this data to the model for predictions. We'll start with borrowers from the positive class. We see that the model managed to flag one of them as a defaulter, but missed the other one, and in fact predicted him as a non-defaulter. Now let's shift our focus to the negative class. In other words, those that did not default on their loans, and we see that the model classified one of these borrowers as a non-defaulter, which is a good thing, but it classified the other as a defaulter, which is a mistake. Because this diagram can get complicated as the size of the testing data increases, we instead use the confusion matrix display. It is just a tabularized form of this diagram. The rows represent the actual class of the borrowers, and the columns represent the predicted class by the model. If we start with the first row, recall that we had 2 borrowers whose actual class is negative, and the model predicted one of them correctly. Because of this, we say the model has predicted this borrower's class to be negative, and that prediction is correct, or true, and we call this the true negative case. In contrast, the model mispredicted the other, so we say the model has predicted this borrower's class to be positive, and that prediction is wrong, or false, and we call this the false positive case. Moving on to the second row, recall that we have 2 borrowers with an actual positive class, and the model has predicted one of them to have the positive class, and that prediction was correct, so we call this the true positive case. In contrast, the model has misclassified the other borrower as having a negative class, and that prediction is wrong, or false, and this is the false negative case. Now that we've constructed the confusion matrix, we can actually move to the metrics used to assess this model's performance, starting with accuracy. Accuracy simply says how accurate our model was with its predictions, and it is the total number of correct predictions divided by the total size of the testing set. In other words, the total predictions. From the confusion matrix, that will be the true negatives plus the true positives divided by all of those cells. In our case, the accuracy is found to be 2 divided by 4, or 50%. In other words, our model is only 50% accurate. That is rather a low value, so we probably want to try another model. The second metric is precision. It simply states that out of any class the model predicted, how often is it right? This definition reinforces the fact that precision has two values, one for each class. The same thing can be said for recall. Recall simply says, out of those belonging to a certain actual class, how many did the model catch? And because the class that we actually care about is the positive class, both the precision and recall we'll calculate are those of the positive class. The precision is equal to the true positives divided by the true positives plus the false positives. In the same way, the recall is equal to the true positives divided by the true positives plus the false negatives. The higher these metrics, the better the model is. In our case, both the precision and the recall of the positive class are equal to 50%. Before I end this video, there are some important notes we have to go through. If your testing data happens to be imbalanced, then the accuracy metric simply becomes misleading. This is because even if the model predicts all borrowers as non-defaulters, it will have 90% accuracy. This is why we don't trust accuracy in this scenario. Instead, we look at precision and recall. Oftentimes, we try to maximize both of them, and that is achieved using the F1 score. In other words, the harmonic mean, which is equal to 2 times the precision times the recall, divided by the precision plus recall. Remember that the precision and recall here are those of the positive class. We do this because there is a trade-off between precision and recall, specifically a trade-off between false positives and false negatives. This can be seen when the model tries to predict all classes as positive. The false positives will increase by default, and the false negatives will decrease. Therefore, precision will decrease, and recall will increase. In contrast, if the model were to predict the whole borrower's class as negative, then false negatives are expected to increase, and false positives will decrease, resulting in a lower recall and a higher precision. Sometimes we bypass accuracy and the F1 score altogether and end up maximizing either precision or recall, depending on the field you're studying. In our example, we aim to minimize false negatives. In other words, we want the model to be harsh and catch more of these defaulters. In doing so, we'll risk flagging some of the safe borrowers as defaulters, which are the false positives. But it is a risk we're willing to take to save the bank from bad loans, and therefore bankruptcy. So we will be maximizing the recall. As a result, the precision will decrease. We'll end this video here. Make sure to visit our website for more practice questions. You will also find other animated courses there. Thank you for watching.